Section 1.3 on radicals. In this section we're going to talk about radicals. So let's get started. Let's first define what a radical expression is. So if n is a positive integer, and let's just write it as a natural number. Positive integer are the same thing as natural numbers. If n is a natural number, okay, and b is a real number such that b raised to 1 over n is a real number, then the nth root of b, so we read this as the nth root of b, is equal to b raised to 1 over n. We came across this in the previous section, in section 1.2, when we talked about rational exponents. So basically that was a radical in essence, because we can write it this way. N is called the index of the radical, and the symbol itself is called the radical. Okay, N is the index of the radical, the symbol itself is a radical. So that is a definition of a radical. Okay, before I give you some examples, let me give you another way to look at it, because I gave you two definitions for this, if you recall from the previous section. So let me do that. We can say that the nth root of b is equal to some number a if a to the n is equal to b. So you can think of that as the nth root of a, because remember, that's how we defined this in the previous section. And since these two are the same, we can go ahead and define the radical in the same manner. So let's take a look at some examples to begin with. Okay, so some simple examples. Okay, let's say that we want to find the cube root of negative 8. That stands for cube root because the index is 3 of negative 8. So basically what we're looking for is some number whose cube is equal to negative 8. And we know that number negative 2 cubed is equal to negative 8, so this number must be negative 2. Similarly, let's say we have the square root of 121. Now, because square roots are used so often, if we don't specify the index, then it's assumed to be square root. So this is the same as just this, 121. So if you don't have the index given, then it's assumed to be square root. So we are looking for some number whose square is equal to 121. And the number in this case is 11, because 11 squared is 121. So that's 11. How about this one? Let's say if I have the fourth root of negative 16. So what are we looking for again? We're looking for some number. If I take it to the fourth power, I'll get negative 16. And again, you should realize this, that that's not possible. Okay, because if I take any number and raise it to an even power, that number is always going to be positive. And we are looking for a negative number, so that's never going to happen. So there's no such real number. Okay, and we can continue this process by this by looking at more examples. But I'm hoping that I showed you what a radical is now, and I gave you some examples, so you should be comfortable with it. Let's go ahead and take a look at some properties of radicals. Just like we had properties of exponential numbers and so on, we have some properties of radicals we need to deal with. Okay, so the first thing is, I'm just going to give you that definition again. The nth root of b is the same thing as b raised to 1 over n. We need to understand that we can switch between a radical and an exponent and a radical. So that's an important thing. the second property is this. Okay, we can say that if n is even, okay, natural number, that means even positive integer, even natural number, okay, and b is a real number. Actually, let me go ahead and write this a little bit more compact instead of being so tedious about this. Let's just do it this way. We say that the nth root of b to the n is equal to the absolute value of b if n is even. Okay. On the other hand, the nth root of b to the n is equal to just b if n is odd. Okay, so these are two properties of radicals. This is one of the most important properties of radicals, so just remember this for the future. So what we're saying here is if n is even, if the index and the power are the same, then you just get the absolute value of b. You get what's on the inside. On the other hand, if n is odd, if the index and the power are the same, you can think of them as they negate each other, and then you just get b back. So that's a great way to write something without a radical. If you want to write something without a radical, we want to make sure that the power and the index are the same, so they will cancel each other and you'll just get the b back. Okay, so that's what we want to do. Alright, the only thing in the first case, in this case, we just want to make sure that we always get a positive number back if n is even. Okay, and I've given you examples of that once before. Okay, so we just want to make sure that that always happens. We always get a positive number back. Okay, in most examples it'll tell you that b is positive or something, so you won't need those absolute values, but it's just to be safe to put them in there. The next property of radicals is if you take nth root of a and multiply it by the nth root of b, then you get the nth root of a times b. If you're multiplying two radicals and the index are the same, then you can multiply the stuff on the inside. The next property of radicals is if you have let's say if you have nth root of a plus the nth root of a, if you're adding two radicals and they're exactly the same, then you just add them like you add variables. We get 2 times the nth root of a. Okay, so if you're adding radicals and they're exactly identical with the same index and the same inside, then we basically just add them and get 2 of those. For example, if this was a 3, then we get 4 of them, because we have 3 here and 1 here, so we would end up with 4. Okay, that's another property of radicals. The next property of radicals is this: if you have the nth root of a over b, when you're taking the nth root of a quotient, you can take the nth root of the top and you can take the nth root of the bottom. That's another property of radicals. Okay, and those are your main properties of radicals. There's lots of other properties of radicals out there, but if you understand these 5, you should be good. Okay, so let's take a look at how to use these properties. Alright, so the next thing we want to do is start learning to use these properties. So this is C. Okay, so the first thing we're going to do is we're going to learn to simplify a radical. A radical expression. Remember, the word simplify basically means we want to make it simple, we want to make it easy on our eyes. So let's take a look at some examples. Let's start with something simple first and we'll work our way up. Earlier I did some examples for you of radicals here. I did some examples that square root of 121 was 11, the cube root of -8 was -2, and so on. We did some simple examples. Now what happens if you have something like this? Let's say if I have square root of 12. Well, what do we want? We want to find some number. When we square it, we'll get 12. Well, let's take a minute and write down all our squares. We have 2 squared is what? 4. We have 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36, and so on. If you notice, 12 lives in here between here. Are there any integers in here between between 3 and 4 that'll give us 12? Whose square will give us 12? No, because there's integer of 3 and then there's 4. There's no more integers in between. So that tells me that 12 is not a perfect square. There's no number I can square and get 12. So 12 is not a perfect square. So if you have a radical where you don't have a perfect square, then you ask yourself, can I write this as a product of two numbers where one of them is a perfect square? So what we want to do is we want to write 12 as a product of two numbers such that one of them is a perfect square. Okay, so let's take a look and see if we can do this. So we have square root of 12. If you recall, square root of 12 can be written as 4 times 3. And then using one of those properties of radicals, when you have a product here, I can break it down into two individual radicals. Okay, so I'm going to do that. I take the square root of 4 times the square root of 3, and we know square root of 4 is a perfect square, so square root of 4 is 2 square root of 3. So square root of 12 is simplified to 2 square root of 3. And that's going to happen more and more. Majority of the times you're going to work with numbers that are not perfect squares or perfect cubes or perfect fourth powers. So then what you want to do is write them as product of numbers that are perfect squares, cubes, and so on. Okay, let's take a look at another example. Okay, let's say that if I have square root of cube root of 54. Okay, now 54 is not a perfect cube, and to prove that, you can check this. I want to find a number whose cube is 54. If you're not sure, just write your cubes down. You have 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. So 54 lives in here between 27 and 64. There's no integer between 27 and 64 whose cube is 54. So that tells me 54 is not a perfect cube. So ask yourself, can I write 54 as a product of two numbers such that one of them is a perfect cube? And here are my cubes, so we can say, does 8 times something give me 54? No, so that doesn't work. How about 27 times something give me 54? Sure, it's 27 times 2. So now I can break it down into the cube root of 27 times the cube root of 2. Cube root of 27 is 3 because 3 cubed is 27, so cube root of 27 is 3, and then I get 2 cube root of 2. So there's 54 reduced to 3 cube root of 2. Okay. One last example, and then we'll move on to some different types of examples. How about we have the square root of 28. Okay. Once again, I want to find some number whose square is 28, and I showed you all the squares here. So if you think about it, 28 lives here between 25 and 36. There's no integer between 25 and 36, between 5 and 6, whose square is going to be 28. So I know that's not going to work. Okay, so there's no such number. So now ask yourself, can I find two numbers such that the product of that is going to give me 24, and one of them is a perfect square? So we're looking for a perfect square. Here are all my perfect squares. Does 4 times something give me 28? Sure, it is 4 times 7. So that works, 4 times 7. So I get square root of 4 times square root of 7. So I end up with 2 square root of 7. So that's how 28 breaks down into 2 square root of 7. Not every number we can do that for. Like for example, if I were to give you square root of 19. 19 is not a perfect square, but there's no way I can find two numbers which I multiply to get 19 and one of them is a perfect square. That's never going to happen, because 19, first of all, is a prime number, so the only other number that you can multiply to get 19 is 1. So that tells me that that's not going to happen. So this radical cannot be reduced. That's all it's going to be. Okay. Sometimes you could also have numbers like this. I have square root of 6. Again, 6 is not a perfect square. There's no number when I square I'll get 6. So I can ask myself, can I write it as a product of two numbers where one of them is a perfect square? Well, 6 can be written as 3 times 2, but neither one of these are perfect squares, so that doesn't help us. So this is the best we can do with square root of 6. So that's reducing radicals, but sometimes they will give you more complicated radicals to reduce. So let's take a look at that. So let's say if I have something like this, if I have square root of, let's say, 50xy squared. Let's just do square root, yeah, y squared. And they want us to reduce this. Okay, so let's take a look at how to go about reducing this. Alright, so we basically, they've asked us to simplify this. We want to write it in the simplest form. Okay, so let's go ahead and do that. So first thing you do is let's worry about the number. Is 50, this is a square root, so is 50 a perfect square? Can I take some number and square it to get 50? No, that's not going to work. So then we ask ourselves, can we write 50 as a product of two numbers where one of them is a perfect square? So I can easily do that. It's going to be what? 25 times 2. Okay, so that's good. Now we want to take a look at the other things. What about these things? Can I break them down and can I simplify them further, just like I'm doing with these numbers? Well, the power of x is 1, okay, and the power of y is 2, so I'm going to leave it alone. What I'm going to do is I'm going to use this property. Anytime you want to simplify a radical, even all these problems that we just did, we were really using this property. Okay, we didn't even realize it, but we were using this property. Let me prove that to you. So let's take a look at this example. Okay, let's take a look at this. We started here, then we wrote it this way, but and then we jumped from here to here. But wait a minute, what happened in the middle? Well, square root of 4 can be written as 2 squared times square root of 3. Now the power here is 2 and the index is 2. When the power and the index are the same, the base comes out, so we get 2 square root of 3, just like we did over here. Anytime the power and the index are the same, the base comes out. Power and the index are the same, the base comes out. So the base comes out of the radical, and that's what we want to do. We did that throughout here too. Like for example, here in this example, we got it to this point, and then we wrote 27 as cube root of 3 times cube root of 2. Since the power and the index are the same, the base comes out, so we get 3 cube root of 2, and that was what the answer was. So you can see we skipped that step, but in this case we need that step, right? So let's see how this is going to help us. Out here there's no way to make this 1 look like 2, so there's nothing I can do, but the 2 out here, the power of y is already the same as the index, so that's good. So now let's simplify this radical. Square root of 25 is just 5, so we get 5, so that's done. Out here the power and the index are the same, so the base comes out, so we get y, and then we get square root of whatever is left. In this case 2x is left. Okay, now I do want to warn you, because the index was even, we still need absolute values, just like we did up here. Okay, remember, if the index is even, we do need absolute values around that base. Okay, alright, so that's what we do with some complicated radicals. Let me give you one that's fairly complicated. Let's say that if I have the cube root of 162, okay, let's not make such a big number, let's pick something small. Let's say 48, okay, times x to the 4th y to the 6th. Okay, now I want to simplify this radical, I want to reduce this radical, so let's start with the numbers. 48 is not a perfect cube. So ask yourself, can I write 48 as product of two numbers where one of them is a perfect cube? All my cubes were right here a minute ago. Does 8 times something give me 48? Sure, it's 8 times 6. That works. So I can write cube root of 8 times 6. That's good. Next, can I write the power as the same as the index? Sure, out here I have x to the fourth. If you recall from the properties of exponentials, x to the fourth can be written as what? X cubed times x to the 1. When you multiply two exponential numbers with the same base, we add the exponent, so we get this. So I can write this as x cubed times x to the 1. How about y to the 6? And the reason for doing that is because I wanted the power to look the same as the base. The index, so I can take that base out. Okay, you always, whenever you're trying to simplify radicals, you're trying to make the powers to look the same as the index. You want the powers and the index to be identical. Okay, so we did that. How about y to the 6th? Well, with y to the 6th, I can do the same thing. I can write it as y cubed times y cubed. Now the powers are the same as the index. That's good, but we can also do this, or we can write y to the 6th as using another property of exponentials. We can go y squared cubed. So you can see the power on the outside is the same as my index. And this is my base then. 2 times 3 is 6. That's a little better way to do that. So I'm going to write that way, y squared cubed. Now, anything that has the same power as the index, the base of that comes out. But before we do that, let's take care of this. Cube root of 8 is 2, so that comes out. The 2 came out. Out here, the power and the index are the same, so this base comes out. So this base will come out. Since the exponent is odd, I don't need to worry about absolute values. Okay. Out here, the power, which is cubed, is the same as the index, so the base comes out. The base is y cubed. Y squared. So y squared comes out. So I'm left with the cube root of, this came out. So we're left with 6x. So that's how that simplifies too. Okay. So whenever you're doing these problems, just make sure you try to use that property. The second property that I pointed out was the most important one. We're trying to write the power of the expression on the inside identical to the index. Okay, let me do one last example and then we'll move on. So let's say if I have the fourth root of 32 times x to the 6th times y to the 8. Okay, so let's take a look at that. Now, is 32 a perfect fourth root? That means, can I take some number to the fourth power and get 32? And the answer is no. So then we ask ourselves, can I take 32 and write it as a product of two numbers where one of them is a perfect fourth root? And in this case, it's going to be 16 times 2, because fourth root of 16 is 2, so that works. So let's do that. So the fourth root of 30, this is going to be 16 times 2. So we took care of that number. Now let's worry about the variables. We want to make this power the same as this index if we can. But that's easy. I can write x to the 6th as what? X to the 4th times x squared, because when you're multiplying two exponential numbers, we add the exponents. So we get x to the 4th times x squared. Then we have y to the 8th. Can I write that as a power of 4? Sure. I can write y squared to the 4. Okay, so I get y squared to the 4. Okay, I could have also done this. I could have written y to the 8 as y to the 4 times y to the 4. That would have worked. But what if I had made this into 80? I wouldn't keep writing y to the 4 10 times like that. So I'll get crazy. Okay, I'm sorry, 20 times. So I'll get crazy. So it's better to, if it was 80, we could have written it this way, y with a 4 outside and 20 on the inside. So just keep that in mind. Sometimes it's better to be a bit more efficient with your writing. So what's a fourth root of 16? That's 2, so that comes out. Okay, so that's done. Out here the power and the index are the same, so the base comes out. Since the index is even, I need to put absolute values, so the base, only the base comes out, not the power, just the base. So that's done. Out here the power and the index are the same, so the base comes out. The base is y squared here, so we get absolute value of y squared, and now that came out. So whatever is left, so we get the 4th root of 2x squared. There's your answer. Okay, so that's how we reduce radicals. As you practice some problems, this will get easier. Alright, so now that we are done with that, let's go on to the next topic. D. Okay, so in this case we are basically going to add and subtract the radicals here, and they could have also basically told us to simplify. That would have been perfectly fine. Okay, they could have asked us to simplify, so keep that in mind. So for example, let's say you have 2 square root of 2x cubed plus 4x times the square root of 8x. I'm adding or subtracting two radicals. In this case I'm adding. Remember the property of radicals that I gave you earlier? If two radicals are exactly identical with the same index and the same insides, then we can add the numbers in the front. So if this is 1, this is 1, we get 2 of those. If this was a 3, we would get 4 of those. If this was a 6, we would get 6 plus 3 is 9. Okay, so anytime you're adding or subtracting radicals, your goal is to make the two radicals the same if you can. If you can, then you can add the stuff in the front. Now for this example, I'm going to make a stipulation. I'm going to say that x is greater than 0. That means x is positive. The reason for this is, now remember, if they don't tell me if x is positive and my index is even, then I need to put absolute values when I take things out of the radical. Out here, if they tell me x is positive, I don't need those absolute values anymore, because the goal of absolute value is to make something positive. If it's already positive, it doesn't need to do anything. Alright, so let's simplify this radical. So we have 2 cannot be broken down any further. It's a prime number, so just 2. X cubed, the index is 2 here, so I want to write this power as 2, so I can write it as x squared times x to the 1, okay, plus 4x. 8 is not a perfect square since we're talking about square roots, so we ask ourselves, can I write 8 as a product of two numbers where one of them is? Sure, we can write them as what? 4 times 2, and then this is x to the 1, so I can't do anything to that power. It's still going to be 1. Now this square root of 2 is just square root of 2, so that doesn't come out of the radical. But out here the power and the index are the same. The index is 2, so the base comes out. So this base will come out, so the x comes out. So we get 2x. That's done. And then I'm left with whatever's left, which is square root of 2x. Plus, out here, square root of 4 is 2, so the 2 comes out. There's already a 4 in the front, so 4 times 2 is 8. And then there's an x, so this came out. Nothing else comes out, so we get square root of x. So now if you take a look at this radical is exactly the same as this radical. When that happens, I can add whatever is in the front. Okay, so in this case we end up with what? 8x, 2x plus 8x is 10x square root of 2x. So there's the answer to that problem. Okay, let's take a look at another example. Let's say that if I have 2b cube root of 16b squared minus the cube root of 128b cubed. Let's make it b to the 5th. I'm subtracting two radicals. The only way I can subtract two radicals is if they're exactly identical. So I need to maybe reduce these first. So let's do that. b to b. 16 is not a perfect cube. Okay, so can I write it as a product of two numbers where one of them is? It's 8 times 2 because 8 is a perfect cube. The power here is 2, here it's 3. There's no way I can make that a 3 since it's already less than 2, so we'll leave it alone. Minus, okay, Over here, 128 is also not a perfect cube, so I have to ask myself, can I multiply anything to get 128? So let's go back and take a look at our cubes here that we had. So here are some of our cubes. Okay, 5 cubed would have been 125, and then 6 cubed would be something fairly big. Okay, 36 times 6. Alright, so it's 216. So 128 is in between here. There's no integers between 5 and 6 whose cube is going to be 128. So it's not a perfect cube. So ask yourself, can I multiply 8 by something to get 128? Sure, it's going to be 8 times 116. Okay, so that works. Okay, but whenever you're doing this, you remember 16 can be broken down further too. 16 can be written as what? 8 times 2. So 8 times 8 is 64 times 2, so we should have used 64 because 64 is a perfect cube. Okay, so sometimes you might have to break things down further. So over here I can write it as cube root of 64 times 2, and then b to the 5, since the power is 5, the index is 3, I can write that as 3. I can write it as b cubed times b squared. Okay, so let's simplify this. Cube root of 8 is 2, the 2 comes out, there's already a 2 in the front, so 2 times 2 is 4b. I'm left with 2b squared, so this came out. Over here, the cube root of 64 is 4, okay, and so this came out. This power and the index are the same, so the base comes out, so you just get a b. I don't have to worry about absolute value since it's an odd the index is odd. So that came out. So what am I left with? Cube root of 2b squared. This radical and this radical are the same, so you add the stuff in the front. What is 4b minus 4b? 0. So the answer to this is just 0. So we started with something fairly complicated and we reduced it down to something fairly easy. Okay. Alright. So that's adding radicals. So let's take a look at the next topic, which is multiplying radicals. Okay, so let's take a look at just a couple examples really quick. So let's say if I have 3 minus 2 square root of 3, and then we have 2 minus 3 square root of 4. I'm sorry, not 4. Let's do 6. Okay, so let's do that. I'm multiplying two radicals. So when you multiply, you basically just distribute is what you do. You take this 3 and multiply it here. You take this 3 and multiply it there. So let's start with that. 3 times 2 is 6. 3 times 3 is 9. So I get negative 9 square root of 6. Then I distribute this, distribute this. We just distribute each of the first terms into the second term. Okay. So when you're multiplying two things that each have two terms, you just take the first term of the first quantity, multiply by the entire second quantity, take the second term, multiply by the entire second quantity. So you get negative 2 times 2 is negative 4 square root of 3. Okay. Let's make this a 2. That'll be more interesting. Okay. And then we get negative 2 times negative 3 is positive 6, and then you can multiply these radicals, so you get square root of 12. So if you recall, the property that we are using is here. If you're multiplying two radical expressions, you just multiply the inside of the index are the same, so that's what we get. So over here, square root of 2 times square root of 6 is square root of 12, and then I multiply the numbers in the front. Negative 2 times negative 3 is positive 6. Now you might be tempted to say you're done, but remember this radical can be broken down further, so we should always try to do that. Okay, so let's do that. Actually, I'm going to go back and change that to a 3. I'm sorry to be a little so confusing, but I'm trying to make the problems a little bit nicer. So this becomes square root of 3 times square root of 6 is 18. Alright, so we get 6 minus 9 square root of 6 minus 4 square root of 3 plus 6. Let's simplify this on the side. What is square root of 18? It's not a perfect square, so we can write it as what? 9 times 2. 9 is a perfect square, so we get 3 square root of 2. So we get times 3 square root of 2. So 18 breaks to that, reduces to that. So we get 6 minus 9 square root of 6 minus 4 square root of 3. 3 times 6 is 18 square root of 2. So there's your answer. If any of these radicals were the same, then we would add them up like we did in the previous examples. Okay. So we are distributing here when we are multiplying radicals. Always use the property that tells you if you multiply two radicals, you can multiply the insides. Okay. I'm sorry, up here we did that, not there. Okay. Let's take a look at another example. Maybe that'll be a little bit easier for you guys to understand. Let's say that if we have 4 minus square root of 3 and we have 4 plus square root of 3. Okay. By the way, these things are called, we have two terms. Okay, here. Anytime you have two terms that are identical, the only thing that's different is in the one in the middle, then we call them conjugates. So the conjugate of this is this, and the conjugate of this is that. So they're exactly identical. The only thing that's different is the sign in the middle. Okay, the only thing that has to be different is the sign in the middle, and they become conjugates. And conjugates are extremely important. Okay, let's multiply this and see what we get. Alright, so we take this 4 and multiply here. So 4 times 4 is 16. Then we take the 4 and multiply here. We get plus 4 times square root of 3. Remember, this 4 is not inside the radical. If this was like this, then I would get square root of 12. Okay, so just keep that in mind. Then we distribute this, so we get negative square root of 3 times 4 is negative 4 square root of 3. Then we get negative square root of 3 times positive square root of 3. We get minus, because there's a positive and a negative, that's minus square root of 9. Okay, because over here square root of 3 times square root of 3 is square root of 9. So we get 16. These two are exactly identical. I have two radicals here that are the same, and this is a positive 4 minus 4, so they will cancel each other. Then you get minus square root of 9 is just 3, so the answer is 13. Okay, so anytime you're multiplying conjugates, you notice what happened. Let me give you another trick that'll make it life easier. Give you another set of conjugates. So let's say you have minus 1 plus square root of 5, and I have minus 1 minus square root of 5. Always recognize conjugates. Are these conjugates? Sure they are. I have two things that are exactly the same. The only thing that's different is the sign in the middle. Don't worry about the sign in the front, just the one in the middle you have to worry about. So these are conjugates. If they're conjugates, if you notice, we went through this whole process of multiplying, distributing, but there's a faster way to multiply conjugates, and there's something interesting that happens with conjugates. All you have to do is, if you have conjugates, you can take the square of the first number, so you take minus 1 squared, which is just minus 1 times minus 1, which is 1, so you write down 1, then put a minus sign, and then you take the square of the second number. What is square root of 5 squared? Well, that's the same thing as square root of 5 times square root of 5, which is square root of 25, which is 5. So you get minus 5. Okay, so you end up with negative 4 and you're done. You don't have to go through this whole process of distributing if you're multiplying conjugates. All you have to do is square the first quantity, then square the second quantity, and put a minus in the middle. That's all you have to do. Now before I go any further, let me point out one note. Okay, two notes. One, when multiplying conjugates, okay, the radical disappears. If you notice in these two examples, I multiplied expressions that had radicals, but after I got done multiplying, did I have a radical left here? No, because we were multiplying conjugates. Anytime you multiply conjugates, a radical will go away. Same thing over here. I multiplied two conjugates, a radical is gone. That's really cool thing about conjugates. Okay. The second thing to note is anytime you square a square root, you just get what's on the inside. And that's because of this property. If you remember, this is the same thing as what? B raised to 1/2 squared, right? Because this is a square root, and I can write that as an exponent using the definition of radicals. And then when you multiply this, you just get b raised to 1. So anytime you're multiplying two square roots, you'll just get what's on the inside, because another way to look at this is, that's one way to look at it. You could have done it this way, or you could have also done it this way. Because of the square, you multiply the two square roots. You take your base, this is my base, and you multiply twice because of the square. So you end up with the square root of b squared. You multiply the inside. The power and the index are the same, so you just get the base back, so you get b back. So this is another thing, it only works with square roots, so keep that in mind. It only works with square roots. So it's a quick way to do that without having to do these little steps on the side done. Okay. Alright, one last example on conjugates. So let's say if you have square root of 2 minus square root of 3, and I have square root of 2 plus square root of 3. Clearly I'm multiplying two conjugates over here. You can see they're exactly the same except for the sign in the middle. So if I do that, all I have to do is take the square of the first. Okay, so let's do that. Let's square this. What is square root of 2 squared? I just told you that if it's a square, if you're squaring a square root, the square and the square root will negate each other, kind of. So you just get 2, put a minus in the middle, and square the second term. What is the square of square root of 3? Square root of 3 squared is just 3, using the same logic as for square root of 2, and so the answer is minus 1. So we no longer have any radicals left. Okay. So that's how you multiply radicals. Sometimes you could have something a little bit more complicated. You could have 1 minus square root of 2 squared. That is the same thing as 1 minus square root of 2 and 1 minus square root of 2. I take the base, which happens to be this complicated thing, and square that. Okay. Now these are not conjugates. They're two identical things. They're exactly identical. Conjugates are when the two terms are identical except for the sign in the middle. So in this case, I'll have to distribute. Take 1 times this, 1 times this. So 1 times 1 is 1. 1 times square root is just 1 square root of 2. Then you distribute here. So you get negative square root of 2 times 1 is negative square root of 2. And then negative and negative is a positive, first of all. And square root of 2 times square root of 2, if they're identical, you just get 2. Because square root of 2 times square root of 2 is square root of 4, and square root of 4 is just 2. So now I can add these two numbers. So I get 3. And I can collect these two because they're the same radicals. I can just add the numbers in the front. There's a 1 here in the front, so negative 1 plus negative 1 is negative 2 square root of 2. Okay, so that's how we multiply radicals. And the last thing we want to do in this section is to divide radicals. So let's do that. Now, there are certain rules in math that we always have to follow. If you remember, one of the rules in math was what? That we could not have negative exponents, because that's how we define the exponential numbers. Another rule in math is you can never have radical in the denominator. Okay, so let's talk about that. The process of eliminating the radical from the denominator is called rationalizing. So rationalizing is just the process of getting rid of the radical from the denominator. Okay, so there are two ways we can rationalize depending upon how the problem is given to us, presented to us. Okay, the first method is when we have only one term in the denominator containing one term in the denominator containing radical. So we have one term in the denominator, okay, that also contains a radical. Okay, so that's what we want to do now. Alright, so let me give you an example of how to take care of something like that. So here's an example. Let's say if you have 1 over square root of 2. I have one term in the denominator, just one single term, and that contains a radical. So what do I want to do? Well, there's many different ways to do this, but I'll show you the method I prefer to teach with. Okay, we're going to use this property that we talked about again and again, that we've been using constantly. When the power and the index are the same, the base comes out. Do we have a radical here? No, we don't have a radical here, so that's what we want to do, get rid of the radical. Okay, so let's do that. Now, to get rid of this radical, what I want to do is I'm going to have to multiply by something on the bottom and the top to negate it, so that eventually I end up with this square root of 2 squared. Why is that? Why do I want that? Because now the power and the index are the same, so the base comes out, so the base is 2. So what should I multiply with that? I already have 1, 2. I need how many 2's here to make it a square? Another one, so I need another square root of 2. So I'm going to multiply the top and the bottom by that. So 1 times square root of 2 is just square root of 2. Square root of 2 times square root of 2 is square root of 2 squared. You can write it as square root of 4, which really is just square root of 2 squared. So we can do that. Now the power and the index are the same, they negate each other, so you get a 2, and on the top we still have a square root of 2. So we got rid of that radical from the bottom. And that's all we do for some problems like that. Okay, let's take a look at another example. Okay, let's say that I have 6 cube root of 9. Now if I had a square root of 9 on the bottom, I would be done, because square root of 9 is 3, and then I have 6 on the top, 3 on the bottom, that reduces to 2. Okay, but in this case I have a cube root. So what do I want to do? Well, somehow I want to multiply by something, so eventually I end up with what? Cube root of something. Before I do that, I should really mention, let me do that first. Anytime you can write a number as a power, you should always do that. It makes it easier to get rid of the radical then. So 9 can be written as 3 squared. Okay, alright, so now let's do that. So what I want to do is I want to multiply by something, so that eventually I end up with this cube root of 3 raised to 3, where the power and the index are the same. When that happens, they will cancel each other, and I'll just get a 3. Okay, and when I say they'll cancel each other, they don't literally cancel each other. I'm just showing you we're using that property. Okay, so now what should I multiply by? Okay, well, I want 3 3's here. I want the power to be 3. I already have 2 of them here, so I just need the cube root of 3. I just need one more 3, because when I multiply, I'll get cube root of 3 squared times 3, which would just be cube root of 3 cubed, because you add the exponents here when you're multiplying two exponential numbers with the same base. So that's why we're just going to multiply by 1, so we get cube root of 3. So this becomes 6 cube root of 3 on the top, and out here we get 6 cube root of 3. 3 goes into that once and into that 2 times, so the answer is 2 cube root of 3. So this is the same thing as this. Okay, remember, we can never have radicals in the denominator, so you need to make sure you follow these guidelines. Let's do one last example. Let's say that I have square root of 5 over 3. Let's make it a cube root. Square root is fine. Let's just do that. So now from earlier properties of radicals, I can break this down into square root of 5 over square root of 3. Can I have a radical in the denominator? No, we can't. So what I want to do is multiply by something. And again, if you notice, I only have one term with a radical here. Okay, so keep that in mind. Okay. So in this case, we're going to multiply by something. So eventually we end up with this square root of 3 squared. So since the power and the index are the same, they will cancel each other and we'll just get the base. So what should I multiply by? I already have 1 3, so I just need another one. Okay. On the top, when you multiply the two radicals, you can multiply the inside, so you get square root of 15. So you get square root of 15 over 3. So that's how we basically get rid of our radicals. Okay. Let's take a look at the second type of problem that we come across when we are rationalizing, where we have two terms in the denominator and either of them can contain a radical. So we could have two terms in the denominator and either of them could contain a radical. Okay, so here are some examples of them. I could have 2 over 2 plus square root of 3. Okay, I have two terms in the denominator, one of them has a radical. Or I could have, let me do another one right next to it. I could have something like this. I could have square root of 2 minus square root of 3 over, I could have 5 minus, I'm sorry, let me do it the other way around. I could have 1 minus square root of 2 over square root of 2 minus square root of 3. So these are your two typical problems you could come across. Okay, I have two terms in the denominator. Either both of them have radicals or one of them has radicals. But the key thing is I cannot have a radical in the denominator. So how do I do this? Now the technique that we developed just a minute ago, when we just have a single term with a radical, doesn't work over here. That only works with single terms. Over here, what we're going to do is what we learned earlier. Remember what I pointed out to you. Okay, right here. When you multiply conjugates, the radical disappears. So that's what we want to do. So since I have two things here, I want to multiply by the conjugate. What's a conjugate of this? Remember I said conjugate is exactly the same thing except the sign in the middle is different. So the conjugate is 2 minus square root of 3. Since we're doing the bottom, we also have to do the top. Then we can go ahead and distribute on the top. So we get 4 minus 2 square root of 3. On the bottom, we can go ahead and distribute, or you can do what we did earlier with conjugates. Remember the trick I showed you with conjugates. When you multiply two conjugates, what do? You just take the square of the first minus, you take the square of the second. So we're going to just do that. What is the square of 2? 2 times 2 is 4. Put a minus in the middle. And square root of 3. What is square root of 3 squared? We talked about that the square and the radical will cancel, so you just get 3. So we get 4 minus 2 square root of 3 over 1. Okay. So that's why I told you about conjugates earlier. So again, out here I have an expression with radical in the denominator. Cannot have that. There's two terms and both of them contain radicals. I'm going to multiply by the conjugate. What's a conjugate of this? It's the same thing except with an opposite sign in the middle. So it'll be plus 3, 2 plus square root of 3, and we'll also do the top. Okay. So now on the top we can distribute. 1 times square root of 2 is square root of 2. 1 times square root of 3 is plus square root of 3. Negative and a positive here, so we'll get minus. Square root of 2 times square root of 2 is just 2. Remember we talked about that. Square root of 2 times square root of 2 is square root of 4, which is 2. Square root of negative square root of 2 times positive square root of 3 is negative square root of 6. Divide that by, we are multiplying conjugates here, aren't we? What happens when we multiply conjugates? You take the square of the first. Square root of 2 times square root of 2 is 2. Put a minus in the middle. Take the square of the second. Square root of 3 times square root of 3 is just 3. Okay. And we can just clean it up a little bit. We can write it as 2 plus square root of 3 minus 2 minus square root of 6 over negative 1. And there's your answer. We don't no longer have radical in the denominator. So that's called the process of rationalizing. So you do need to have a good understanding of that, because that's something we do a lot of. And so the more you're comfortable with it, the better for you in the long run. Okay. Alright, let me just do one last example with some variables and rationalizing. It's the same idea though, so it doesn't change any. Okay. So let's say if I have x minus square root of 3, let's use something different we've been using, divided by x plus 2 square root of 5. Okay, so they could have just told you to simplify this, because simplify means you want to make it easier, and one of the things that makes it easier is if you don't have radicals in the denominator. So I want to get rid of this radical. I have two terms in the denominator, so I want to multiply by the conjugate then. So the conjugate is the same thing except the sign in the middle changes. So I'm going to do the same thing on the top. Okay, so let's go ahead and do that. So you distribute on the top. X times x is x squared, because you take x times x, you're multiplying two exponential numbers with the same base, you add the exponents. 1 plus 1 is 2. X times this is negative 2x times square root of 5. Okay, because I have negative 2 here, that comes here, and then I have x, and then I have square root of 5. Same thing over here, you distribute this. Negative square root of 5 times x is negative x square root of 5. Remember, these are not inside the radical, so we can't multiply them on the inside. Okay, and then negative times negative is a positive 2 times, what is square root of 5 times square root of 5? Just 5. We've talked about those. Okay, because square root of 5 times square root of 5 is square root of 25, and square root of 25 is 5. And in the bottom, what do we get? The bottom is easy. Since we're multiplying two conjugates, we just square the first. What's square root of x? It's just x squared. Put a minus in the middle, and you square the second. What is the square root of 2 square root of 5? So you squared 2, 2 squared is 4, and then you squared this, you just get 5, so you get 20. And we're not done, because we can add these guys up because they're the same radicals, and we can add the stuff in the front. So we get x squared minus 3x square root of 5 plus 10 divided by x squared minus 20. Okay. So there's your answer for that problem. So I hope you understood the concept of radicals, and if you practice some problems, that understanding will become long-term and will be better for you, because we do these little simple things with radicals of we do the simple idea of rationalizing quite a bit. Okay, so if you understand that, it'll stick with you for the long haul.